this quiz is just to kind of make you aware that there are different schemes for the periodic table, depending on the publisher of it. And one of these you might think is dated, this Roman numeral system, but it's very useful, actually, the Roman numerals. So I'm going to give you a chance to correct the quiz and resubmit it if you'd like. So I'll hand this back today. And we'll probably have another quiz today. All right, so chapter 2 deals with matter and energy. So that's what constitutes the universe, right? Matter, which is the physical material of the universe, and energy. And why we're interested in energy, which isn't considered matter, is because, make sure this is recording. Yeah. It's because matter's interaction with energy. All right, so let's take a look at the learning objectives. These are the SLOs. And so Prakalici does this. Let's do this. Okay, so first one, identify and explain the differences between interpreting and describing matter. There are different ways we can describe matter, but normally when a chemist thinks about matter, we can see it here, or sometimes we can't really see it, like the air in this room. Can you see it? No, but it's there. I mean, there's other ways to detect it. So visually, we can see things that are at the macroscopic level. And so when we describe things at the macroscopic level, we can actually see it. Although we can see that this room is full of air, otherwise we wouldn't be able to breathe. And so in that sense, we see it. But also at the microscopic level, sometimes we look at crystals. Sometimes these crystals are very small. Like, have you ever looked at table salt? And then see what's the what we call the form. There's color. When we look at something, we look at the color. Like this table's black. But do you know what is the color of table salt? It's white. But have you ever looked at an individual grain? That individual grain of salt we call a crystal. Have you ever looked at the crystal of salt closely? You probably could see it with your naked eye. You probably don't need a microscope. But if we had a microscope, you could see it probably more clearly. And do you know what the color of that individual grain of salt is? Pink. Pink would be like sea salt or something like that. But like the packaged salt that you'd have over at the fast food place, or not blue, not pink. So nobody's really looked at a single crystal of table salt. It's colorless. You could actually see through it. So it appears white. And then when you get up close, you can actually see the color. And so color is kind of important for geologists for identifying minerals. But the thing is, color can be deceptive. Sometimes it could look white, sometimes it looks colorless, right? And no, it's interaction with light, just the interaction with light energy, and that's what we detect. There's a couple of seats here. We should have enough seats. Are you guys registered for the course? Yeah, you could grab this seat here. It's empty, and there's one seat in the corner over here. You can just move it if you'd like. So since color is deceptive, what you need the same size grain. So in geology, they have the scratch test. What they do is they take a porcelain plate, and you're supposed to scratch the crystals to make a fine powder. And then when you look at the fine powder, that's what you determine as the color. So if you have a big crystal, it might look slightly different in color than tiny fine crystals. So you want to be consistent. You want to always compare things that have similar form. Then you can detect if there's a color difference or maybe get a more accurate read. So at the microscopic level, we might be doing that, but we really don't spend much time talking about the microscopic level. For us, we're just interested in the macroscopic level and something called the particulate level. What's the smallest particle of water that you can have called? a molecule. And the smallest particle of salt you can have, what would that be? Sodium chloride? Yeah, but we need to give it another name because, you guys know that salt is sodium chloride. It's made up of the sodium atoms and chlorine atoms, and we call it sodium chloride. But the smallest particle of salt, would we call it a molecule? True or false? False. So we call it sodium chloride, but we need something more descriptive. And that, you know what the more descriptive one it would be called? It would be called a formula unit. A formula unit is just the smallest unit that you can have for whatever you're looking at. And so, for example, water, what would the formula unit for water be? It would be H2O. And what do we call that? We call it a molecule. But what would we call the formula unit of salt? We would just call it a formula unit. We wouldn't call it a molecule. And let's take a look. You can see that when we look at structure. Do you see what this is? This is a tiny, tiny drop of water. You probably can't even, you wouldn't even be able to see this with your naked eye. But this is what we call simulation. Let me try to pause that there. Well, when we try to visualize things, we try to visualize that at the particulate level. So this would be an individual particle of water. These spheres here represent hydrogens. This one represents oxygen. This stick here, this is a vibration. This stick here, it just shows the attachment that they're bonded together, but there's no stick attaching it. The atoms be like this, clustered together. These are two water molecules. Those are individually separate. They can be separated into individual particles that we call molecules there. So that would be two molecules of water, or two particles of water, or two units of water. Now, these water molecules, they look kind of stuck together. They like to stick together. Water likes to stick with other water molecules. And so, otherwise, things like a swimming pool wouldn't exist. And so this would be a bigger cluster of water molecules. This cluster would be so small you wouldn't even be able to see it. It's so tiny. But you can see the water molecules kind of sticking to each other. And this would be liquid water. In liquid water, they're kind of stuck together. That water molecule that just flew by, that's gaseous water or water vapor. So there's some humidity. These would be gaseous water molecules here. Even at room temperature, some water molecules have enough energy to do this first, especially at a higher temperature. At a higher temperature, you have more, what type of energy? Does anybody recall the type of energy? Kinetic energy. So I mentioned kinetic energy the other day, and so what we're saying here, this is called molecular dynamics here. These are different molecules here. These are individual particles, or no, not benzene. This is nitrogen here. And so we try to visualize things at the particulate level, what's happening at the particulate level. This is something called molecular dynamics, where we can use the theory. The theory of chemistry is used to predict such stuff like this, because that's the power of the theory. The power of the theory is you should be able to predict new unforeseen results. This is why people want to understand the theory and refine the theory. Ultimately, we'd like the theory. You can make predictions with a law, but you aren't going to have as broad of let's say as broad of a window into the chemical world with laws. And so with theory we can. And so these are all theoretical predictions of how these things should behave at particular temperatures. This has been slowed down also. The time scale has been really slow motion. This is slow motion. And the time scale might not even be, let's see if usually molecular dynamics, you can see the time scale here. But, so this would be a mixture. The difference between pure versus a substance, actually pure is a substance. And so what was I thinking? The difference between what and what? A substance and a mixture. A substance is going to have a fixed composition and fixed property, whereas a mixture like sugar water won't have fixed property because the properties of sugar water will depend on how much sugar you put in the water. You put lots of sugar or a little bit of sugar in water. And so these are atoms of different elements, and there are about 120 elements. Not all of them are equally abundant. Some have been synthesized, but don't last very long. They're quite unstable. These are different representations. This is a representation of DNA here with sticks only, no balls. And so we can represent, or we could represent it using ribbons. Ribbons just show the backbone of the DNA. So this is more useful for large molecules. For large molecules, lots and lots of atoms involved. Sometimes to get a better feel for the structure, we have pleated sheets and helixes and ribbons, etc. Molecular dynamics. So at this level here, at the particulate level, we can see more what's happening versus at the macroscopic level. But we look at both levels quite in detail, and we look at properties at both levels. So we want to identify and explain the differences between interpreting and describing matter at the macroscopic, which you can see, versus the particulate level. So when I look at a liquid like water, I can see that it's a liquid, but I can kind of imagine what's happening with the particles. The particles are moving around, the water molecules are stuck together, this kind of stuff. Define the term model as it is used in chemistry to represent pieces of matter too small to see. So those are models there, molecular dynamic models. And we have models, we have actual plastic balls and plastic sticks that we can make of these molecules. And, we can draw them on paper. All right, identify and explain the differences among gases, liquids, and solids in terms of macroscopic properties, shape and volume, particle movement, and particle spacing. So we'll look at that as well. Distinguish between physical and chemical properties at both the particulate level and macroscopic level. And so this is where we hone in. Microscopic, we never do. Just the macroscopic and the particulate. Distinguish between physical and chemical changes in both. So what's the difference between a physical change and a chemical change? Give me an example of a physical change. And when I say physical change, we're talking physical properties. So tell me the difference between a physical property and a chemical property. Physical properties sometimes they involve physical change, not always. Like color really doesn't involve any physical change, but some properties that involve physical change would be melting point, boiling point, that type of thing.
I guess like physical change could be like when you leave a glass of water out the sun, there's a it would change from a liquid to a gas state.
And then what else is key about that?
It would be that it changes states of matter.
Yeah, it changes states of matter, but when it enters the gaseous state, is it still identified as water, or did it change its identity?
It's still water.
It's still water. Did the atoms rearrange? When we talk about matter rearranging, the matter didn't rearrange. It's still there. It did rearrange in one sense. That is, when we think about water in the liquid state, the water molecules are stuck together. But if you heat it, what's going to happen? They're going to get more kinetic energy, which is going to break the water molecules apart, which will vaporize them. And so at one level of structure, it's broken apart. At the other level, the water molecules are still water molecules. They're just now in air. Versus a chemical. Tell me about a chemical change or chemical reaction. What happens there?
It's called the elements inside that substance change, like H2O, like H2O, like not specifically water, but like those elements elements alter.
Ye-
Increase number, decrease number, something like that.
Yeah. The substance changes. How did the substance change specifically? How did the substance change?
Interaction with other elements.
Yeah, interaction, and then what changed? At the particulate level, what changed? Uh-huh. What makes up the substance? What makes up substances? Elements and elements, but we have to be more specific. Try to imagine this at the particulate level. The not because not everything's made up of molecules, but everything is made up of atoms. And so, what happened to the atoms? Did some new atoms come, and some atoms disappear? You know, some atoms converted into phlogiston, and this invisible vapor just wisps away. What happened to the atoms? So that's what we want to understand at the particulate level. What's happening? You know, how does the substance change? And the answer is that the atoms get rearranged. All the atoms are still there, because we have a conservation of mass, which says what? The law of conservation of mass says. I'm sorry? Okay, that's conservation of matter, which we can get from conservation of mass, since matter is anything that takes up space and has mass. So, yeah, conservation of mass was that mass doesn't change. You know, all the matter is still there, and then therefore the conservation of matter. You know, matter is neither created nor destroyed. That's a law. Laws we can still use. So if I have a physical change or chemical change, those laws apply. So if I start off with 10 grams of water and boil it all away, will I still end up with 10 grams of steam, or did some of it disappear into phlogiston or something like that? What is the answer? If I have 10 water molecules in the liquid state and I vaporize them, and how many molecules would I have in the gaseous state? 10. Would you expect to have 9, maybe, or 8, maybe 2 of them disappear? Or would you have extra, 11 or 12, because some appear? No, so this conservation of matter at the particulate level. And so we need to understand that here. Distinguish between a pure substance and a mixture at both the particulate level and the macroscopic level. We have different types of mixtures. We'll talk about this. Distinguish between homogeneous and heterogeneous matter. Describe how distillation and filtration rely on physical changes and properties that separate components of mixtures. Distinguish between elements and compounds. Distinguish between elemental symbols and the formulas of chemical compounds. Distinguish between atoms and molecules. State the law of definite or constant composition. What is the law of constant composition? Not the structure. Structure, because what 3 things do we look at as chemists? Well, we look at nature, but what about nature? What do we
Observe it.
we observe? Or what do we observe with nature, and what do we try to understand? Yeah, we try to look at patterns. This would be the scientific method, but ultimately, what we want to know is how these 3 things are correlated, and what are those 3 things that we'd like to correlate?
Like structure, composition, and properties.
Yeah, structure, composition, and properties. And so, structure and composition we treat separately because, for example, do you know what diamonds are made out of? Carbon. And do you know what graphite's made out of? Graphite used to be made out of lead. Well, I mean, lead pencils used to be made out of lead, I think, because lead is a very soft metal. And so if you scratch it, you can leave a trail of lead atoms. But they're made out of carbon too. So what's the difference? Pure graphite is made out of 100% carbon. Diamond is made out of 100% carbon. The composition's the same. So what's the difference? The structure is different. How the carbon atoms are arranged are different. And so the law of constant composition It doesn't talk about structure. It talks about the third leg, which is composition. I gave an example. Does anybody remember the example I talked about yesterday? Uh-huh. H2O, right. I said something about pure water in like California. Does it have the same composition of pure water in New York? Well, that's the difference between a substance and a mixture. Tap water in California, does it have the same composition of tap water in New York? No. But what about pure water? Pure water in California, would it have the same composition of pure water in New York? And would you say that pure water in New York would have 3 hydrogens instead of 2 hydrogens, or what would you say? I mean, do they call it H3O in New York, or do they call it H2O? Why should they call it H2O if it's a different composition in New York? Is it a different composition in New York? No, it's not. It's the exact same because it's pure. Whereas mixtures, like say, if your friend made sugar water and you made sugar water, are you going to have the exact number of sugar molecules? No. So mixtures don't have definite or constant composition. The mixtures have variable composition. So we'll talk about that briefly. Okay, and this continues on here. This chapter goes through a lot of different topics. Match electrostatic forces. Have you ever heard of electrostatic forces? Electrical forces. You've probably heard like magnetic forces. Like if you take 2 magnets, and you bring the 2 north poles together, what happens? They separate. They repel each other. It's like the same thing happens with electrical forces. If you take a positive and try to bring them together, do you know what they do? They separate too. They repel. Versus if you take a north pole and a south pole, then what happens? They attach. They attract. And the same thing, if you take a positive and a negative, they attract. This is what they're called electrostatic forces of attraction and repulsion. Chemistry is, all electrical forces. So what holds the water molecules? Why are they sticking together? The water molecules sticking together in water is because of electrical forces. Distinguish between reactants and products in a chemical equation. Distinguish between exothermic and endothermic changes. Exothermic and endothermic changes deal with energy. This is matter, and undergoing some of these changes can absorb energy, and matter undergoing some of these changes can release energy. And these changes could be both physical and chemical. So an example of a physical change where it absorbs energy would be like melting ice. If you want to melt ice, what do? You add energy. What if you want to freeze water? What do? You take away energy. You need to slow it down so it freezes. This also happens in chemical reactions as well. Like when you burn wood, does burning wood release energy or does burning wood absorb energy? Do you have to heat it up? Absorbing energy would mean you'd have to constantly add energy to get wood to burn. But it's kind of weird. We'll talk about it some more later, but it actually releases energy. And so the surroundings around the combustion of wood become hotter because of the kinetic energy. I'm sorry? The environment around it's getting hotter. No, the combustion of wood is releasing the energy, and the surroundings around it are absorbing energy. So if you stand around a fire, you're going to feel the energy coming off the burning wood. Versus if it were absorbing energy, you would get cold. standing in front of a fire because it's taking heat away from you, taking energy away from you. And, we have names for that. If it releases energy, we call it exo. Exo means external. Endo means internal here. And so exo would be losing energy to the outside. Endo would be gaining energy on the inside. Distinguish between kinetic energy and potential energy. So somebody just mentioned kinetic energy. What is kinetic energy related to? Moving, motion. But there's another type of energy that involves no motion, and we have to think about this. Let's say I had a stationary lead brick, so there's no kinetic energy; it's not moving. But if I put the lead brick on the floor, okay, it's not moving; it has zero kinetic energy. What if I put the lead brick on the ceiling, hang it there? It's not moving, so it has no kinetic energy. It's not moving. But what would you rather have, a lead brick on the floor or a lead brick on the ceiling? On the floor, because what's the difference? The potential energy. The lead brick on the ceiling has the potential to fall down and hit you in the head, whereas the lead brick on the floor doesn't. And so that's called gravitational potential energy. And the higher that brick is, the more you got to worry about it falling down and causing some serious damage. And so that's the difference. Now, this is not a physics class. This is a chemistry class. But the same thing goes with chemistry. Let's say kinetic energy, we think about in terms of temperature. Temperature is a measure of the average kinetic energy. So if it's 25 degrees C, 25 degrees C they call room temperature, which corresponds to about 77 Fahrenheit, which is a little warm for me, 77. I don't know what it is in this lab room, but is it a little warm in here? Yeah, it's too warm in here. This is more than. But it's warmer. What happens? We got more kinetic energy. What happens when we have more kinetic energy? We get more motion. And you could be uncomfortable. Now, potential energy. So let's say we had two things at 25 degrees C. If we take two things at 25 degrees C, which we call room temperature, quote unquote, and it's not necessarily meant to be the temperature of this room. It's just what people call room temperature, or the average room temperature, whatever. Yeah, Celsius, or 77 Fahrenheit. Two things at 77 Fahrenheit, let's say. They both have the same kinetic energy. So there's no difference in the kinetic energy. So let's say I have two things. One, you could put some carbon dioxide and water. And so you have a container of carbon dioxide and water, which you might call sparkling water, in your car at 25 degrees C. So sparkling water versus, let's put a container of methane, oxygen in your car. What would you rather have? A container full of methane and oxygen, or a container of CO2 and water? CO2 and water, why? It's not going to react. I mean, CO2 and water is pretty unreactive. It's pretty what we call stable. I mean, people will drink it. Versus, would you want to fill your car up with methane? No. Would you want to fill this room up with methane? No, because what happens if somebody accidentally sparks or there's a hot surface it comes into contact with? It'll explode, right? And so methane is normally odorless, but they put an odorant in methane to make it smell bad. Otherwise, we could accidentally fill this room up with methane. And every year, do you know, every year there are buildings destroyed by methane explosions, including, what was it, some 5-story apartment building in New York City that there was a methane explosion there. And so we have to be careful. And so what's the difference? We say the difference is in potential energy, but it's not gravitational potential energy because methane and oxygen is not hanging on the ceiling ready to drop down, right? But it's a different type of potential energy, and that different type of potential energy is the potential chemical potential energy. It has the potential to explode. The CO2 in water can also explode. I mean, you get pressure thing going, but it wouldn't be nearly as violent. And it would just be based on the container. Maybe the container's too weak to contain the sparkling water. Maybe somebody shook up the container. If somebody shakes up the sparkling water and then opens the cap, what's going to happen? It's all going to kind of explode out of there, but it's a totally different type of explosion. It's a pressure thing. And so these are two important topics, and we need to keep those separate. And we always keep them separate in our mind, kinetic versus potential energy. And we know references to that. All right, just like we have the conservation of mass, state the meaning or draw conclusions based on the law of conservation of mass. We also have the law of conservation of energy. State the meaning and draw conclusions based on the conservation of energy. So there's certain observations that show that energy is conserved, just like mass is conserved. All right, so we're going to just jump into this now here. Matter is everything that has mass, all the physical material of the universe. Most of the matter that chemists deal with are made up of the atoms of the elements there. And so there are 120 different elements. And so those would have different properties depending on the, when we look at the composition, structure, and properties of the atoms, of the elements, we'll see that there's differences in the composition and structure, giving them differences in behavior. And so therefore we have the periodic table. The periodic table is extremely useful. There's a lot of information that we can gain from the periodic table. We have this new numbering system from 1 through 18, but we have an old system with Roman numerals. And the old system is quite useful. No. Okay, so at the macroscopic level, consideration of matter on a scale observable by the human eye. Geologists study matter at this level. Actually, geologists study matter at all levels. A lot of geologists use electron microscopes. So I wanted to study the surface of some stuff I made when I was at UCSB, and so I started talking with the geology department about using their electron microscope. We look at tiny crystals and mixtures and this kind of stuff. I actually never went ahead and did that, but it turned out it wasn't necessary. Microscopic, skip that. Basically, we need a microscope. A microscope would be like a optical microscope versus there are other types of microscope that can probe at much deeper level. For example, a scanning electron microscope. Have you ever heard of that? Or scanning tunneling microscope. The scanning electron microscope, or an SEM, or a scanning tunneling microscope can actually probe things at the particulate level. Whereas an optical microscope is just at the microscopic level. And so there are some microscopes that are powerful enough to probe individual atoms, to see them. I mean, when you see them based on an output from a computer. You don't see them visually. People are trying to see atoms visually. They're trying to see atoms visually, just like we see things. When we see things, light hits it, creates some kind of diffraction pattern, and our eyes have lenses, and what do those lenses do? They take that diffracted light and refocus it into an image. In order to see atoms, we need X-rays, and what that means is we need lenses that would focus a diffracted pattern of X-rays. The problem is nobody has been able to develop a lens to focus X-rays. If somebody could develop a lens to focus X-rays, then we could use X-rays and the lens to see images of atoms, just like we would see an image of a lake or image of a mountain with our eyes. Uh-huh.
So what's the smallest microscope?
With a what? With a microscope? With a an atom, an individual atom, with a scanning electron microscope. Well, it depends on how you define see. You can see it with an instrument. You can see it with, it would be an electrical output. And here, let's take a look. This is the surface of gold using a scanning tunneling microscope, it looks like. Or it might not be gold, it could be graphite. Let me see. So there's just a very fine tip on this, and it just probes the surface. And it deals with electrical interactions, like repulsions and this type of stuff. So it tries to maintain a constant repulsion. And so that means in some places it can get deeper, in other places it has to go further in order to maintain a constant repulsion, what we call a constant voltage. And so this is how they can probe individual atoms. Here, if the tip is fine enough, you can see this. And so this is an image of atoms. I asked you this. In science, we have to have, what? In the scientific method, we have to have, if you come up with a hypothesis, we need what? We need some kind of support, some kind of evidence for that hypothesis. So if somebody proposed that, let's say the coronavirus came from bats and then transferred to pangolins or whatever, and then transferred to humans, we need some supporting evidence. So, for example, did they find the coronavirus in the wet market in Wuhan? Where a lot of animals infected there. Do you know how many animals they found that were infected with coronavirus at the wet market in Wuhan? 0. But that doesn't mean it couldn't have happened, right? It just takes one instance. But we want some supporting evidence. And so what was the evidence in support of the, maybe, I'm sure it came from bats, but, how the actual method of, why do you want to know? A lot of people don't want to know, but why would you want to know? Why would you even care? Why you would care is because you don't want it to happen again, right? I mean, whatever happened, it shouldn't happen again. And in order to understand how not to happen, how to prevent it in the future from happening, you need to understand, how it happened in the first place. And so, anyway, we need supporting evidence. And so it becomes difficult, because if you have some things, you have tons of evidence, and it's so easy. So if you want to prove that atoms exist, throw it in the scanning tunneling microscope, probe it, take one of these atoms and start breaking apart. An atom smasher. You take an atom and break it apart in an atom smasher, or a cyclotron or glider or something like that, where you can get tremendous kinetic energies. So much energy that the atoms smash together and break into fragments. Do they break into tinier atoms of gold? No, you know what they break up into? They break up into things called subatomic particles, protons, neutrons, and electrons. You probably already heard of those before. And those protons and neutrons can be broken up into further smaller pieces called quarks. You know, so you can try to smash it in smaller and smaller pieces, but the smallest piece you can smash it or observe it in is the atom. And so this is the smallest particle of gold. I'm pretty sure this is the surface of gold. Uh huh.
So when you said, on the atom smasher,
Yeah.
when you use that, you can't see anything?
No, it's no longer gold. It doesn't have the properties of gold. It's not a gold atom anymore. It's consists of protons, neutrons, electrons, quarks. What's that? Those, yeah, those aren't visible with a microscope, but they're visible using other detectors. And so there are ways to detect those electronically. I'm sorry? Yeah, those are particles of matter. Um, those would be even finer particles than this. But for chemists, when we think of this, we look at water, and then we look at what is the smallest piece of water we can have. But you know that water can be broken apart. If you take that water molecule and put it into the plasma of the sun, what happens? Well, it'll evaporate long before it hits the plasma of the sun. But let me stay on the side. These are all solids. When you probe these things with a scanning tunneling microscope, they have to be solids. You can't probe gas or liquid because it's moving around too much. And so, long before it evaporates into gaseous water, which is still water, steam, the humidity in this room, which is kind of humid in this room, that's still water particles, water molecules in air. Nothing's changed still. But if you take those water molecules and particles and then put it into the plasma of the sun, then what happens? There's too much kinetic energy. You know what the temperature of the sun is? I told you room temperature is what, 25 degrees C? We're talking millions of degrees C on the sun, right? In the sun. And it can't survive. There's too much kinetic energy. Molecules can't survive in the sun. Yeah. And so what happens is it breaks apart. So the hydrogens break apart from the oxygen. But in the sun, it doesn't. The individual atoms themselves don't get smashed. There's not that much energy to do that, And so we have other pieces of the atom break apart, but in essence, they kind of stay together. And so it's still hydrogen, still oxygen, but some pieces called electrons break off, and but the protons and neutrons don't. It depends on the amount of energy. In atom smasher, you get higher energies. You know, you get higher energy, so you think it's the power of the sun, but you're only looking at individual molecules. The sun is huge plasma. So if somebody's asking you for evidence in support of atoms, it's easy because in the modern world, there's a ton of evidence in support of atoms. It wouldn't be very difficult to prove to somebody that atoms exist. It would be very easy to prove. But did Dalton have a scanning tunneling microscope? Did Dalton have an atom smasher? No, he didn't. And so how did Dalton prove? Because it was a hypothesis. It's just a hypothesis. It's just like the lab leak hypothesis versus the animal hypothesis. You're trying to convince the other side that you have the correct. It doesn't matter. People aren't tied. Although on those two hypotheses, it was more. I mean, usually scientists are pretty objective. They don't care. They just want to know which to support because it has the most evidence to support it, and they don't care about politics or whatever else. They just want to know which one has the most evidence to support. So how did Dalton prove? How did Dalton convince other people to accept his theory? I mean, not theory, because a theory, remember, a theory has to have widespread acceptance, support. So in order to become a theory, he had to convince other people that his hypothesis was correct. And so when we look at what evidence there is to support that particular hypothesis, what evidence is there to support the what particular hypothesis? What led to the theory in the first place? I mean, how did the theory become a theory, or how did the hypothesis become a hypothesis? What led to it? This is the scientific method, and this is what scientists do. Yeah, the patterns. Based on those patterns and trends, then it's like you're trying to solve, some crime, and you're looking for, certain patterns or whatever in support. Maybe you get it right, maybe you get it wrong. Ultimately, you'd like. And if you don't have enough evidence, then you state you don't have enough evidence to conclusively state this. People were already, even before there was enough support, people were already divided into camps, over certain hypotheses, and completely ignoring any evidence to the contrary. If there's evidence to the contrary, you want to know it. And then you want to say, well, this is the reason why the evidence is being interpreted incorrectly, this kind of stuff. And so,
How did he even prove to everyone else that Adam was wrong?
That's very difficult, isn't it? Because he didn't have all these tools we have nowadays. So how did he prove it? And he was correct. He was correct. The other people were wrong. The other people, you know what the other camp was? The other camp was it was infinitely divisible. So if you have a chunk of gold, you could divide it into smaller and smaller pieces, and it would never end. And so the smallest piece of gold would be infinitely small. And so what evidence did those people have versus what evidence did Dalton have? You have two competing hypotheses. I don't care which one's correct. I just want to know which one to adopt, right? Just like, I mean, you don't want to have a personal. I don't have a personal attachment to atoms. If atoms didn't exist and was infinitely divisible, what difference does it make to me? I just want to be convinced with proper evidence that I should support this or that, or maybe there isn't enough evidence. Maybe we're still debating it. Are we still debating it? According to my junior high school teacher, we aren't. But when my junior high school, did I tell you about this in middle school? In middle school was the first time I heard about atoms, and I just believed it outright because, my science teacher told me that atoms exist, therefore I believed atoms exist. But it doesn't work that way in science. In science is you can't just say atoms exist and that's the end of story, period, right? It has to be, you have to have some evidence and support. And so if you propose some hypothesis, you're going to be grilled. I mean, this is the way science works. I said there's no scientific policeman. There's no one person who defines science. Science is a collective, and where there's always the skeptic, and everybody's skeptical. You should be skeptical of both hypotheses. Maybe there's a third hypothesis that somebody didn't think of. Maybe there's a third culprit in the theft or the murder or whatever else in the crime saga, right? You don't want to be, oh, that person did it, end of story, period, convict, that kind of thing. You want to see all the evidence in support of that or contrary to that. And so you don't want to hide evidence. Do you want to hide evidence because it doesn't support your case? Which unfortunately happens. Yeah, why did Alton put it together in the first meaningful theory? And that's what we need to know, and that's why, before it becomes a theory, it has to have widespread acceptance. And so you're relying on other people that, they accepted it, and therefore, but that's not, if everything was already done and known, then there's no need for new scientists. Right? Because everything's already figured out. Somebody has it all figured out. Why become a scientist? And so everything you do, you have to think in terms of, okay, what's the skeptic going to say? When when you publish a scientific article, there's two types. One is called peer reviewed versus non-peer reviewed. Peer reviewed is like you're sending it out to other people to check it. Usually you send it out to experts in the field. And so what you do is you write your paper, and then it gets sent to these reviewers called referees, and then they go through and scrutinize it heavily, and then you get it back. And so there's a long delay between when you submit the paper and when it's actually published. A lot of people don't like that long delay because it could be months. It depends on how long it takes for the referee to get back. And then sometimes when you get the paper back, it says, well, you need to do more experiments here. It's unconvincing. And so then it takes even longer. And therefore, the peer review process is lengthy and there's a time delay. During COVID, though, and even pre-COVID, people want to circumvent that because they think, okay, I have some important information, but it needs to be more timely. We can't wait for the peer review process. So those are called communications, and these happened well before COVID. And so communications aren't normally peer reviewed. They just send them out and they just publish it. And later on, some skeptic might say, oh, this is wrong. This is totally wrong. And then sometimes things are missed, even by the experts in the field. Do you know about the NASA astrobiologist? The NASA astrobiologist, and they're looking at life forms on other planets, and the other planets might have a different elemental makeup. I mean, other planets are made up of the same elements, but we might have more of this or less of that. And so they're looking for extreme environments on Earth. And so one of the extreme environments on Earth is a lake in California, Mono Lake, which is near Yosemite on the northeastern part of California. And Mono Lake, there's no fish. The only thing that lives in Mono Lake are brine shrimp. And there are lots of seagulls because seagulls like eating the brine shrimp. Yes. But one of the reasons there's no fish is because of the high arsenic level. There's a lot of arsenic in Mono Lake. And so the brine shrimp are surviving in that environment, I think, and also bacteria. And so this NASA astrobiologist said, well, arsenic, do you know the symbol for arsenic? Yes. Element number 33. Yeah. Arsenic, and he's not that has a taste gas. He is another element, phosphorus. When they're in the same column, they're in the same family. So arsenic and phosphorus share similar properties. Phosphorus is an important molecule in life. There's energy. We talk about chemical potential energy, and there's a molecule that we rely on for energy, and it's called ATP. ATP is an energy molecule. And ATP can be converted into other forms, and then it's exothermic. It releases energy, and that energy we can use to do things with. It's like food. Food contains a lot of calories. It has energy. What kind of energy? It's not kinetic energy. It's potential energy. It's the potential to be consumed, digested, and release energy exothermically. Well, this NASA astrobiologist thought, since there's such high arsenic levels, maybe this bacteria is an arsenic-based versus a phosphorus. We're phosphorus-based life. We're phosphorus-based life because we use ATP, that's an energy molecule, in our mitochondria or whatever. Maybe the bacteria have an analogous one, but it's not ATP. It would be ATAS. ATAS would be an arsenic versus a phosphorus energy molecule. So this NASA astrobiologist proposed that it's an alien life form on Earth. Now, it would be terrestrial, but it would be alien because it's not phosphorus-based, it's arsenic-based. And so this This was published in Nature magazine. Nature magazine is one of the hardest magazines to publish because when you send it out, the referees are very harsh. If it doesn't meet a certain standard, they reject it. When they reject a paper, then you have to look for other magazines to publish in. And so Nature is one of the most respected. In fact, Nature Nature is not U.S. based. Nature is based in the UK. U.S. based would be Science. Science magazine and Nature magazine are the two most rigorous and most difficult journals to publish in. Other journals, they let a lot of stuff slide through, but this was published in Nature in 2010. But unfortunately, I mean, it's exciting to predict your monolith. This is very exciting. I thought this was, I remember when this paper was published because I thought that was big news. That's pretty cool. Because if there is an arsenic-based life form, then there could be lots of different kinds of life forms, you know, although it's just bacteria. Could be different kinds of life forms on other planets and stuff. So I thought it was really cool. But unfortunately, it turned out to be untrue. And so what happened was the initial referees didn't catch it, but later on, people were scrutinizing it. There's still a lot of skeptics. You have to convince. Can you imagine how much scrutiny this paper received? It was very heavy. And finally, somebody figured out they couldn't repeat this. They couldn't get it. And they finally figured out it was unfortunately a problem of contamination. And the arsenic didn't actually come from the bacteria. The arsenic came from an external source. It was by accident that it got contaminated. But anyway, this is how science kind of polices itself because it might not have been caught initially, but eventually it was caught. And then yeah, I think there's a lot of pressure. There's a lot of pressure. But that was published in, I think that was published in Nature. Or was it published in Science? Sorry, it's been 14 years ago. Science. Okay, it was published in Science. That'll make sense. It's in the US. Published in Science in 2010. And so the bacterium in arsenic-rich monolith was said to redefine the building blocks of life, surviving and growing by swapping phosphorus for arsenic in its DNA and in cell membranes and whatever else. There's phosphorus in DNA, ATP, cell membranes, etc. So this is why I say phosphorus-based versus arsenic-based here. Biologists consider these 6 elements as necessary for life. Carbon, we're mostly carbon, I think. Or actually, maybe hydrogen and oxygen because we have a lot of water. We can look at the percentages of carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur in our bodies. Arsenic was similar to phosphorus because it's in the same family, but it's typically poisonous to living organisms. Anyway, the original study needed to be confirmed in order to be considered a true discovery. So, 2 separate teams found that indeed the bacterium needed some phosphate to survive and could not fully substitute arsenic to live. And so, unfortunately, it was found to be untrue. I'm sorry? Yeah, brine shrimp. But the brine shrimp are phosphorus. They could tolerate the high arsenic. Arsenic is kind of an interesting story because arsenic was used for murder for centuries. You know, it depends on how you're exposed to the arsenic. They have cases where people had blood levels of arsenic that were so high they would have been lethal to like 99% of the population. But it turns out they had a little bit of time, so they were building some kind of tolerance against arsenic, so they could have these extreme arsenic levels. And so there are lots of things that can survive in that. It's not. But of course, don't drink arsenic. There's arsenic in food, you know. There's arsenic in foods like rice and a lot of other foods, and so we could tolerate certain levels of arsenic, you know, but high levels are definitely bad for you. There's certain standards of how much arsenic can be contained in food. You know, of course, you don't want to be at the limit of those particular standards because it's kind of high. It's like there's certain limits to how much radiation there could be in food. So if there's radioactive rice, or there's arsenic-containing rice, you know, they can tolerate it up to a certain point because they figure, okay, you can survive this. You know? But anyway, one paper was written by this Princeton University folks, and this is kind of interesting. Life's building blocks. You know, the atoms are the building blocks of matter. And, the composition of DNA and the structure of DNA. And, well, anyway, the bottom line is that this paper had to be retracted. That happens. There are lots of papers that have to be retracted because new evidence comes in that refutes the support. And so, how did Dalton do it? You know, Dalton had plenty of retractors. How did he do it? How was he able to convince people? Well, he must have had some strong supporting evidence. What was the strong supporting evidence? Because these people are pretty serious skeptics. They don't just take somebody's word. You know, Dalton probably was a respected scientist. They just aren't going to take his word. They want some evidence and support, you know. And they didn't have anything against Dalton, you know. Sometimes when you go to the conferences, you think, wow, that person has like some kind of personal vendetta against that because they're grilling them, but it's not. You know, sometimes you see people grilling them just because they're really curious and they want to know, you know, how does it support. So I'm sure Dalton had plenty of people grilling him. So how was he able to convince those skeptics? What's that? Yeah, he proved them false. Exactly. Right. So this NASA astrobiologist was being grilled, because a lot of people thought this is doesn't seem to make sense. I mean, yes, it makes sense, but it doesn't make sense. It doesn't make sense because if you know some chemistry about arsenic versus phosphorus, the bonds holding the atoms together are much weaker in arsenic. And so it doesn't take as much kinetic energy to break those bonds. You know, like water is pretty strong. You throw it in the sun, yeah, it's going to break everything apart. But arsenic, you wouldn't even have to throw it in the sun. You know, maybe something less extreme could break it apart. There's some things that are so fragile they break apart very easily. Like just being exposed to light will break apart. Or mechanical, just a hit like this will break it apart. Things like hydrogen peroxide. Hydrogen peroxide is stored in a brown bottle, like iodine. Iodine's stored in a brown bottle. It's a brown bottle so that no visible light hits it. Because if visible light hits it, then it's going to break apart. It's like photographic film. In the old days, they had photographic film and they had the dark room. And the dark room had red light. They had red light because red is weak energy light versus white light. White light has all the colors of rainbow. So if you hit it with violet light, it's going to expose the film. And so they had those types of things. All right. So the challenge here was you can't see particles without special tools. And so this makes Dalton's job particularly difficult. So what are the scales? Now, what we say is these atoms are really, really small. You can't see them, but scientists like to be more quantitative. We want numbers. So how big are atoms? And so we need some kind of reference points. One of the reference points is we should have a number about how big atoms are. And so approximately how big are atoms? If you look at this, atoms are on the order of 10 to the minus 10 to 10 to the minus 11. Here's a water molecule. A water molecule is about this big, 10 to the minus 10 meters. 10 to the minus 10 is a hard number to remember. And so the number we typically say is this. 10 to the minus 10 meters has a special name. It's called an angstrom. And so atoms are about 1 to 6 angstroms in diameter. There's another unit we could use, and it's called a picometer. You know, it's way smaller than a micrometer. Micrometer, we use a microscope, is 100 microns, 10 microns, 1 micron. 1 micron would be like a bacteria cell. Viruses are a bit smaller on nanometer scale. Molecules are very large molecules. Proteins are very large molecules. This is shrunk down. This would be way bigger than the aspirin. This is an aspirin molecule here. This is a water molecule here. These are individual particles. Individual particle of protein, aspirin, water, and then the atom. These aren't all on the same scale, obviously. These atoms are blown up. So how big are atoms? They're around here. Atoms are in the 100 to 600 picometer or the 1 to 6 angstrom range. And so we should know that. We need an electron microscope to see these kinds of things. An optical microscope won't. An optical microscope will take us to a bacteria cell. Scanning tunneling microscope will take us to individual atoms. And that's what the image was produced over there, the scanning tunneling microscope. All right, let's take a break over 15 minutes. We'll meet again at 11:15. If you missed roll, let me know. So normally a periodic table is given. They don't usually have the name. Like this one has the name here, and so that's helpful. But most of the time, you're going to have to memorize the names. You're going to have to memorize the names of at least the first 1, 2, 3, 4. At least the first 4 rows. But then there are a whole bunch of other elements in here that we'll have to memorize. And so you just start memorizing these if you don't already have them memorized. A lot of them are intuitive. You can kind of figure it out. Others aren't so intuitive and will require a little bit more work to determine. What elements do you need to have memorized? So let's take a look at the supplement in lab manual. So this is well, you'll have to get from the bookstore or find it. Supplement in the lab manual. Supplement is supplemental instructional material that goes beyond the textbook. And so there's some stuff that the textbook doesn't have that you should know. And other stuff you might just want to just go through nonetheless. And so the first part of this starts off with the supplement. If we look at the contents here, of math review, measurement, formulas, quantum numbers, reactions, net ion equation, oxidation numbers, electrolytic voltaic cells, strength, adaptation bases, supplementary columns. These are all supplemental sections. And so these go beyond what's in the book. So for example, the book doesn't even talk about quantum numbers much. And so to help the transition from Chem 4 to Chem 1.8 become smoother, we have an introduction to quantum number here in the supplement. Then we have the labs. The labs are in the second half, and so this is the first half here. So this is math review. All these should be straightforward. And so just go through and make sure they look pretty easy. If not, just work through them. And so simplify each mathematical expression. One thing that's different is this would be like physics and chemistry. In math, oftentimes they don't worry about the units. So units here would be kind of weird. It's inches times inches plus feet. Inches plus feet don't add up. Let's say somebody is 5 foot 5 inches. Do you just take 5 plus 5 and 10? You get 10? 5 plus 5? No. And so we worry about the units here. We call these the dimensions. So this is dimensional or unit analysis. This one's okay. Foot-pounds is the dimension of torque. So miles per hour is the dimension of speed. This would be kind of weird because both of those are length, but they're in different units. This would be a micrometer squared with the square root. And this would be millimeters cubed divided by millimeters would be millimeters squared. That would be area. This is kilogram meter squared per second squared. Kilogram meter second squared is actually a unit of energy. It's like lifting a 1 kilogram mass by 1 meter against the force of gravity, which is that's how that quantity of energy is defined. And we have a name for this. A kilogram meter squared per second squared is defined as a joule. A joule is similar to a calorie, but it's just the size is different. There are 4.18 joules for every calorie, so it's a little smaller than a calorie. A calorie is just a unit of energy. We could have like potential energy. That candy bar has the potential energy of 100 calories, something like that, 200 calories. Here's a unit mismatch, liters and milliliters. You can't just subtract those numbers. So when we have a unit mismatch like this, here and here, we have to convert one into the other. So we either express length in inches by converting feet into inches, or we express length in feet, converting the inches into feet. And the same thing here with the volume. And then we have unit conversion problems like microliters. 25 microliters is equivalent to how many milliliters. This mu, this is the Greek letter mu, which stands for micro, and m, lowercase is milli. Capital M, you know what that stands for? Mega. So this would be megagrams too. Little m, do you know what that stands for? Nanograms. So megagrams, nanograms. Here's square feet and millimeters squared. These are meters cubed to liters. So we're going to go through some of these. These are some tools that we use. One of the biggest tools that we use in problem solving is something called dimensional analysis, which we'll use to solve all these problems. This is chapter 3, by the way. And then we have measurement. This is how to take measurements. Here's some practice. Where do you measure? The top or the bottom? This is a thermometer. In the case of a thermometer, we measure from the top of little, what we call meniscus. For volumes, we measure at the bottom of the surface of the liquid is curved. It can either be curved down, concave, curved up, convex. We either measure it at the peak or the valley. Let's look at some practice measurements. Measurements are our experiment next week. So those are practice problems. This is what you have to start memorizing now. So you can, actually, I would like you to know the whole third row. The first, second, third, and fourth row. Some of these, like Cr, the chromium, the Mn, manganese, the Fe, a little harder to guess. Why do they do that? Why didn't they use IR? Could have used IR because I is used for alone as for ID, but I don't know why. The same thing with sodium. Why didn't they use SO for sodium? Hmm? Yeah. Why didn't they use Latin word? Why didn't they use the English word? I don't know. I had a student that always wrote sodium chloride as the name for NaCl is natrium chloride. So it depends on where they are. So you'll see that. But anyway, these are important ones. This is the minimum that you should know. Yeah. Things like gold, the symbol for gold, AU. That's from Latin. And so start working on those here. You have to get the correct spelling too. So for example, fluorine is often misspelled. A lot of people spell fluorine as FLORIN. Uh-huh.
When you say memorize the chart, do you mean just the symbols and what the names are, or do you have the numbers?
You don't have to memorize the numbers. Memorizing numbers is not necessary. Because my memory's so bad, I took a online course. This guy has the world record for memory. I was listening to his lecture, and one of the lectures, he was talking about how he memorized all the numbers of the elements in the periodic table. All the numbers, the names, and the symbols. But I thought that's not very useful. Is so what? You know what element number 80 is? Does it really matter? Not really. You know what matters more? Can you? Because he didn't mention this. Did he memorize what family it's in? Element number 80. What family is that? What other elements are similar to element number 80? So we take all that raw data and we come up with patterns. The periodic table came from patterns of chemical properties and physical properties, physical and chemical properties. And it was organized based on that. As we go across the periodic table, the properties change gradually. It has to be metal, and it changes gradually until we get to krypton. Krypton is a nonmetal, so it goes from having metallic properties. What are metallic properties? Metallic properties, metals have luster, they conduct electricity, they're great thermal conductors. They react in chemical reactions by typically losing electrons. They have loosely held electrons. Electrons are these subatomic particles I talked about earlier that make up atoms. Whereas nonmetals, their properties vary more, but one thing is they typically don't conduct electricity unless you're looking at graphite. Graphite is a nonmetal that conducts electricity quite well. They undergo reactions where they typically gain electrons, not lose, except for the noble gases. The noble gases are faster too. So there's certain characteristics and properties that we grew. So these change gradually as we go across a period. The period is called a row. And then within a family here, one member of this family is missing. That's important. What's below phosphorus? You know what's below phosphorus? Arsenic. And so that's where that came up. And this is where the NASA astrobiologist was starting to think, yeah, if the planet's full of arsenic, why not an arsenic-based life form? Yeah, there's a staircase here that's not shown. That staircase is on the dividing line, but it's not black and white, it's gray. And so there's transition from metals, like this is considered metal, and then you go through what are called semi-metals on the staircase, like silicon. Aluminum is a metal, silicon is not. Well, silicon is a semiconductor, but it's the transition here. That staircase is kind of the border between the metals on the left, which there are a lot, like gold, etc., lead, and the non-metals. There are a lot fewer non-metals than there are metals. a lot of metals, including what we call the rare earth metals. Have you heard of the rare earth metals? The rare earth metals are down here, the actinides, and the lanthanides, the rare earth metals. That's another name for these guys. Yeah. The lanthanide. But there's other things that are missing here that you should probably know. But at a bare minimum, this would be it. So work on these initially. So how do you memorize stuff? You know, I have bad memory, so I've tried lots of different things. I've tried flashcards, but the problem with flashcards is, is when it came to the exam and I had to write it down. Like, what was the symbol for whatever, copper? I had to write it down. I couldn't get it to click. And so what I did was I did this. If I had a list like this to memorize, and it was a hard one, like let's say gold, I would just write it over and over again. I would write it over and over again so I get it into my motor memory. And once it was in my muscle memory, then if on an exam I was asked to write the symbol of gold, it just come out automatically, AU. I've written it so many times, it's burnt into my motor memory. And so I recommend that. I found that to be quite a bit more effective than flashcards. Other people use like Quizlet. If you like Quizlet and that type of stuff, you could do that on online to get it. But you'll have to be able to write the symbol and the name. Now, the name is a bit trickier, because it takes a lot longer. I found if I write it repeatedly, like 50 times, depends on how hard it was to remember. 50 times is usually enough. Over, like a drill, you just write it over and over again. Some of them require more, 100 times, 500 times. If you wrote it 500 times, maybe it should stick into your motor memory. But like names, like fluorine, some people spell it Florine, that's wrong. Or FLOU, like flower, flowering, that's wrong. How's fluorine spelled? FLUOR. Make sure. What else is commonly misspelled? Manganese. A lot of people actually put magnesium for manganese. Potassium. A lot of people put just one S rather than two S's on potassium. A lot of people think, okay, K is krypton. Well, krypton is actually Kr. And P is potassium, but P is not potassium. P is phosphorus. Now, this numbering scheme, the 18, I don't find all that useful. The Roman numeral scheme is much more useful for us. And so you should know the Roman numeral scheme. It's pretty easy to figure out. So this periodic table doesn't have it, so it's missing it. This one doesn't have it. This one doesn't have it. This one has it. This is a periodic table on. Oh, this one doesn't have it. So we want one that has it. Oh, I don't want it. When we do the Roman numerals, there's an A versus a B. So this block of elements, this one's called the alkaline metal, this is alkaline earth, is 1A, 2A. Then it skips over this whole block here. You see there's this gap. And so when we go from B, which is 4, and we go to B, which is boron, at 5, it's a huge gap. And so it goes here 2A, and then it jumps to 3A over here. This would be 3, 4A, 5A, 6A, 7A, and then the noble gases would be 8A. This is the Roman numeral 8A. And so this is what, or 8, because there's no 8B. Now, when we look at the B's, here we go from calcium, which is 20, to scandium, which is 21. There's no gap there, so it's going to go 2, but we already used 3A, and so we're going to have to use 3B for this series across here. And then something funny happens. You go to 7B here, but look at what happens here. 8. These three, iron, cobalt, and nickel, are all Roman numeral 8. Why is that? They're all 8Bs, yeah, but why are they all the same Roman numeral? Yes, exactly. They have certain properties that are similar. And that's why the Roman numeral scheme is more useful, because if it's 8, 9, and 10, you wouldn't even know that they have similar, this one property. And then take a look at what happens here. This is 1B. Why is this 1B and this is 2B? You know why? Because they have similar properties as to what? They have similar properties as to 1A and 2A over here. Who designed this? Many scientists designed this. Mendeleev, one other person, came up with the first periodic tables. Those are like in the 1700s. And they designed it based purely on observation. And when something's based purely on observation, we call it what? It starts with an E. What's that word? Empirical, good. This is another thing about memory. Memory is this is world record holder, and not only that, I read books when I was a student at UCLA about studying. But you lose, how much memory do you lose? You lose it over time. And so let's say you went to a lecture or a presentation. The next day, how much of it would you remember? Let's say you didn't write anything down. How much would you remember? Like, they say you forget like 60%. And so that's like, oh, I missed 60% of the lecture. Why even bother going? You only went for 40% of it. If you're going to lose it the next day, right? So that's why people write stuff down. So, and that's what this memory expert said. There's a certain interval that you need to review it. So if you go to the lecture, you write it down. The next day you review it. And the next day you review it. And then the more frequently you review it, then you can spread out the intervals. So let's say 1 year later, do you need to review it every day to retain it in memory? No. And then he has different intervals he set. And so at 1 year, you should review it like every 1 month, I think. I actually forgot because I didn't write it down and I didn't refresh my memory, but something like that. And then 10 years later, how often do you have to review it if you want to retain it? Now, this becomes very important because let me tell you about my friend. My friend, the bio major at UCLA, was reviewing chemistry for the MCAT. But he took chemistry his first year at UCLA. I was a transfer, but I was a chem major, so he came to me for help. And now he was graduating senior, so it was like 4 or 5 years later. I can't remember exactly. I think the average time is 5 years now, maybe 4. Anyway, so he asked for help to review chemistry. So I sat down with him to go back and review some chemistry. Do you know how much he remembered? How much he remembered? 0. He remembered nothing. And so it was like starting over again. And so there was no way he would be prepared in time for the MCAT. And so he gave up. He just gave up on taking it. So what he did was he took not 1 gap year, he took 3 gap years to review everything he forgot, as a student. He spent all that time. He spent 1 full year taking chemistry, or general, and then another full year taking organic chemistry, and had forgotten everything by the time he went to go take the MCAT. And now he had to go back and do it all over again. That's like, like Sisyphus pushing the rock up, and it going down and not making any progress, So he had to go back and review all that stuff. And Fortunately, he was able to do it, but I wasn't able to help him. But he had tutors to help him review that. But anyway, getting back to this, if we have a periodic table like this is great because you have a lot of additional information that you can get, certain properties from. And so this is why the Roman numeral scheme is quite useful. These 8s don't correlate, so this is not called 8b, this is called 8. This is 8, but there's no connection here between this 8 and this 8, whereas there's a connection between these. And that connection we'll talk about, but there are two ways to approach the periodic table. The periodic table was not generated from theory. The periodic table was generated from observation. So Mendeleev looked at the properties, and he grouped certain elements into families. And then these are the families that we have up now, today. Mendeleev's time, there were fewer elements filling it out, but most of the families were there. That's empirical, but do you know this table can also be generated from the opposite end? In science, we can approach things empirically from observation, but we can also approach things from the opposite end. What do I mean by the opposite end? The opposite end of the scientific method, which would be from theory, right? And so this table can be generated theoretically. By understanding the theory of chemistry, you can generate this table without knowing any of the properties, without knowing any of the observations. And that's another great thing about the theory, because the theory should be able to predict. And so could it predict the periodic table without knowing any observations? Yes, it could. The periodic table, there are lots of different forms. This screwed up thing, whether it's 14 or 15 elements here, depends on how the periodic table is arranged. It's kind of screwed up because the page is not wide enough. And so if they have it properly done, they wouldn't have these holes here. These aren't really holes. They're actually filled. But it's kind of... But it's a little bit more complicated. You can see from the theory how it works. So we'll talk about how it works when we get to the theory underlying the periodic table. But first, in order to do anything, you have to do some memorization. So we need to memorize the elements, but this is very minor. Memorizing these element symbols and names should be very easy. We're going to have to memorize much more difficult things than this. And the much more difficult things are things that we call polyatomic ions. Those are more difficult because, let's say, do you know what the formula for hypochlorite is? Do you know what the formula for hypochlorite is? Bleach. Bleach is sodium hypochlorite. And so, I know like sodium chloride is salt. What is bleach? Bleach is NaClO. And other things. What's the formula for ammonium nitrate? So we have a lot more stuff we need to memorize. So knock this out of the way quickly. This should be fast, and then you can start working on the harder stuff to memorize, which we're going to jump into pretty soon. This is a lot easier to memorize. There's certain patterns in the periodic table here and I try to memorize patterns. Like, for example, here, what's the pattern here in the first column? So they're all one class, and these are called ions. What happens is you have enough kinetic energy not to destroy the atom, but you have enough kinetic energy to knock a piece off. And the piece that you knock off is an electron. And so if we knock off an electron has a negative charge. And we're going to be missing that negative charge, which means there's going to be a positive charge. There's something called electrical neutrality. The amount of negative charge matches the amount of positive charge. And another pattern, these are all +2. And then another pattern here, +2 and +3 are here, followed by +1, +2, followed by +2. Now, do you see why there's Roman numeral 1, 2 here? There's a reason there's Roman numeral 1, 2 here, because +1's common here and +2's common here. And then here plus 3. This is Roman numeral 3. You know what Roman numeral this column is? 4. You see, look at the charge. Now, Roman numerals we can extend here, but this is easy to see why these are the way they are, which we'll talk about later. But there are patterns here. We memorize the patterns. So I wouldn't do this with flashcards. I do this by the position of the periodic table. If the periodic table is written on the wall, then I already know. What are the plus 2, plus 3s? I know what area in the periodic table plus 2s or plus 3s are, so I don't have to memorize them individually. When I was a student in Chem 4, I had to memorize them individually. What was iron? I had to write iron 2 plus, iron 3 plus. I had flashcards for that. And so that was more difficult. What was copper? Copper was plus 1, plus 2. I memorized those when I was taking Chem 4 as a student. And that was difficult for me because flashcards didn't do it. I couldn't remember. I had to get it in my motor memory, so I had to write it down over and over. But rather than writing it individually, individual observations, I look for patterns because patterns are a lot easier to remember. And so if I know the patterns on the periodic table, I've saved myself a lot of flashcards and a lot of writing. So I just need to know what region they are. And so if I have an element here, what do you think it is? Charge. If I have an element here, what is its charge? Plus 2, plus 3. If I have an element here, what do you think its charge is? Plus 2 and plus 4. If I have an element here, this is not enough. This is plus 3, plus 5. This is group 5. If I have an element here, this is plus 2, plus 6. I mean, minus 2, plus 6. We'll talk more about it later. So this is additional stuff. I don't care how you memorize it or how you understand it, but you're going to have to know the standard charges on the element. Like a pre. We haven't gotten to the charges yet, but memorization for me takes time. So the earlier I get started, the easier it is. If you do this every day, then it'll be easy. By the time the exam comes, you'll have it down. But if you do it right before the exam, the night before the exam, then forget it. It's just going to be overwhelming. It's going to be like a tidal wave of information you need to memorize, and there's just not enough time. You know. So this is the way I used to memorize it. Cobalt. So I'd have a flashcard, cobalt plus 2, cobalt plus 3. I'd have a flashcard for its name. Cobalt Roman numeral 2, parentheses, cobalt Roman numeral 3. Not only that, I had to memorize these. When I was a Chem 4 student, I had to memorize cobaltus and cobaltic. You know, what was cobaltus? And so on the test, we had a question, cobaltus, write the formula. And I'd be thinking, you know, it'd be hard because I had the flashcards. I didn't have it in my motor memory. But then I eventually put it into my motor memory. And then I was able to do it. But if we have that. Now, the Alice and the Ig, these are old forms. So I'm not even going to make you guys memorize. I had to memorize these, but I'm not going to make you guys memorize them because these are falling out of favor. You know, it's much more in favor of the Roman numerals. And the Roman numerals are easy. If you know what the charge is, you know what the Roman numeral is. Or the charge. And so that's less memorization. If you find it difficult to memorize stuff, then you want to get an early start. You don't have to understand what, you just have to memorize it. And later the understanding will come. Yeah. But the more understanding we have, the less memorization we have to do. And so you look for patterns. And you don't need to know the hypothesis. You don't need to know the theory to use patterns. You can just go ahead and use patterns to make predictions. Now, certain things are a little bit tricky, like this one. Mercury 1 is a weird one because it's an Hg2. Now, the subscript means we have 2 atoms of mercury, Hg. And the total charge on this is 2 plus. So if we have 2 atoms of mercury and the total charge is 2 plus, then each mercury is 1 plus. This is what we call it mercury 1 because each atom is 1 plus. And so we see these patterns here that we can use to help memorize certain things. So these are what we call the cations here. These are monatomic except for mercury. Mercury would be a diatomic, but it's the same element. Then we have the monatomic anions. These monatomic anions, we just look at the pattern of the periodic table. So I don't even bother making flashcards and memorizing this. I just look at the pattern on the periodic table. I memorize the pattern on the periodic table. I can figure out. The names we'll talk about more later. The names are going to come in the next chapter, chapter 3, I think. And we're going to start with the names. Okay, these ones are a bit more of a pain to memorize. So I asked you what the formula for hypochlorite. Well, this is the formula for hypochlorite, ClO, 1 chlorine bond. I might ask you, what is the formula for perchlorate, sodium perchlorate? And so this, a lot of people have a thick stack of flashcards. Look through. I don't. What I do is I look for a pattern here. Do you see any pattern here? Maybe. But sometimes we think, oh, maybe the ones that end with an ATE, 8, have 3 oxygens. But then here's an 8 that has 4 oxygens. And then there are 8s that have varying numbers of oxygens. This kind of stuff. But there are patterns there. I'll talk about the patterns there to minimize. So in essence, you see a lot of stuff to memorize here. But in reality, as long as you have the periodic table, you can get a lot of these off the pattern in the periodic table. So the actual number that you have to memorize, even flashcards or whatnot, is about 5. 5 of these I have to memorize. The rest I can figure out based on patterns. They're more than this that I want you to know. Our book has a different way of doing it. Krokalichi recommends memorizing the acids. So he recommends memorizing the acids and then figuring out everything else based on the acid name. I don't do that. I've never done that. If you find that more more understandable way of remembering these, then use Krokalichi's method. I'm going to approach it totally different than Krokalichi in this chapter. I have a different preference. But eventually you're going to know all these. And you'll have to know these by the first exam. And so this is why I kind of want to forewarn you in advance to maybe get started memorizing these. And this is like learning a language. You know, you'll have to memorize some of the vocabulary here in order to speak the language, to speak jargon. In other words, you know, if you don't know what sulfuric acid is and the formula for that, then as you go on in science, it'll be more and more of a sore thumb. I mean, it'll be very surprising for a lot of these. Okay, so get started on that. And then, like I said, quantum numbers is stuff that's not talked about in the book. And therefore, this supplemental chapter was written for quantum numbers. So this talks about quantum numbers, like 5 pages or something. Here's a table of quantum numbers. So if we find a pattern like this, the pattern is a lot easier to remember, right, than memorizing individual. The formulas? The page numbers are screwed up because each section is numbered for that particular section. And so the formulas are in section formula, and the page numbers are formula 1 through formula 4. And it's on the upper right. Yes. But memorizing the strong acids is not that difficult, it turns out. There are only 7 of those. And what that does is that the 7 common strong acids, it does is means that everything else you can assume to be weak, although there are more than 7 common strong acids. We're going to ignore the others, so we're going to simplify it a little bit. That one, you don't have to know that for the first one. That would be more chapter 16 or chapter 5. Chapter 5, we're going to have a table. The table is going to have a ranking of acids. And there you can just look at the table and then just see what the strong acids are. Not only do we need to know the strong acids, we need to know the relative strength of the weak acids. And there, we don't memorize it. We just use a table. Some things you can figure out based on structure, which should be stronger, which should be weaker. But we're not quite at that level. And so the initial hit of memorization comes with the nomenclature. The second will come from chemical properties, where you're going to have to do a little bit of memorization. Not as much as the nomenclature, but you will have to memorize certain things. So the quantum numbers, there's memorization involved here. What is the N, L, M, S, and what are all these other things here? We have to memorize not only those types of things, we have to memorize this. You have to be able to draw this. This is extremely important because this comes from the theory of chemistry. This is the basis of the periodic table right here. The first column, actually it's not grouped into columns, but they can be, is here. And then actually the first two columns are here. And this would be the last 6 columns here. And this would be the first 2 columns plus the middle 10 columns plus the last 6 columns there. And each of these is a row or a period. And so this is the periodic table right here. It's just in a different form. And so, if you know that that's the periodic table there, then it's a lot easier to draw this, because you could just look at the periodic table and draw it by hand, if you make that connection, versus just memorizing this outright. And so by the time we get there, hopefully this will make more sense, but nonetheless, you have to be able to recreate this. Just to the fourth, what we call the 4th period. The 4th period would be that 4th row across, from starting with element potassium all the way to krypton. So we start off with potassium here, and we end up with krypton over here. We'll talk about this more later. But we're not going to do the 5th row. The 5th row would be this, the 6th row, the 7th row. This is the entirety of the periodic table here, and then it goes beyond that. Actually, it's already gone beyond this because people have developed elements all the way to 120. Okay. And actually, there are an infinite number of these. We'll talk more about that. When we have an infinite number, obviously you don't want to memorize an infinite number, so we have mathematical patterns. These mathematical patterns will allow you to determine that infinite number of these states. Here, we call these states. It's easier to memorize when you do a bunch of these, and you have to do a bunch of these. So that makes it easier. And so these are some exercises and these are questions here. These are the answers to the questions here. And then these are some practice problems with the periodic table and that chart you just looked at here. Here we're looking at chemical properties. So what happens when magnesium is burned in air? What's happening with the matter? What's happening with the atoms? How are they being rearranged? And so when magnesium is burned in air, what happens? Well, we need to describe what happens. We describe what happens by using formulas. The formulas tell us the composition. They don't necessarily tell us the structure. Well, we want to see how the composition of these things change. That is, how the atoms are rearranged. So, for example, H2O is water. H2O2 is hydrogen peroxide. So there's difference in the composition and the properties. Magnesium oxide is added to water. Sulfur trioxide gas is bubbled into water. Do you want to memorize these one by one? Because how many different reactions occur in nature? If you just think about your human body, how many different chemical reactions are occurring in your human body right now? A lot. Do you want to memorize each individual one? In biochemistry, you have to memorize a lot. In biochemistry, when I took it, we had to memorize the tricarboxylic acid cycle, and other stuff. And so, I thought, that was a bit of work to memorize that. You might think, why? Memorization is so old-fashioned. But if you can't talk to somebody, about chemistry, and the other person doesn't understand what you're talking about sulfuric acid, and the other person doesn't even know what sulfuric acid is, then it's hard to communicate. And so you have to have a certain basic language level. It's like trying to communicate to somebody who doesn't speak English, you know. And if you don't have this, at least a certain basic level memorized, it's going to be very difficult. So these types of things we'll learn. And learn, hopefully we can minimize memorization, because even though there's like an infinite or a seemingly infinite number of potential reactions that can occur, we can break those down into types of reactions. So somebody was asking me what the chemical properties of hydrogen peroxide are. I don't know, was it in this class or the afternoon? It must have been this class, right? So do you want to list them one by one? It's potentially an infinite number. No, so what we want to do is we want to look for patterns of reactivity, and that's how we make predictions, using patterns of reactivity. This supplement's very long. Okay, not only do we have these 17 here, then we go on to net ionic equations. And so here we're trying to get a deeper look into how these occur structurally, how the atoms are rearranged, type things. And so we have a bunch of these, what are called net ionic equations. And then we have something called oxidation numbers. Oxidation numbers from the periodic table, these are very useful. Like, I want to understand the properties of hydrogen peroxide and look at the oxidation numbers. And I want to look at what it reacts with, then I look at the oxidation numbers. And so there's some practice. And then the final section of this is electrolytic and voltaic cells, batteries, and that type of stuff. This is also covered in chapter 19, but this goes into a little bit more depth here compared to what chapter 19 does. And so we have a chart like this. Then we go to acids, base. Normally when we're doing like chapter 16 and chapter 5 stuff, you get a chart like this, because this chart's going to rank the strength. So for example, trichloroacetic acid versus acetic acid, which one's stronger? Or oxalic acid versus chlorous acid, which one's stronger? You can figure out theoretically, but it would be a lot of work. And so what we're going to have is we're going to have this chart. This chart is just empirical, which one's stronger. Now the 7 common strong acids are here. And so you're using this chart so much, and then you'll learn the names of it. Like, for example, the top acid for chloric acid, followed by hydroiodic, hydrobromic, hydrochloric, sulfuric, chloric acid, and nitric acid. Those are the 7 common strong ones. And most people don't find those too difficult to memorize. All these other ones are weak. But we'll be using that chart quite a lot. This is the answer key to all the problems in the supplement. And then finally, we have the lab manual. And so the first half is the supplement. The second half is the lab manual. We're going to do today's lab. Today's lab is going to be the laboratory burner. Let me make sure I have enough time for today's lab. And then next week we're doing measurements. Trial law. We're skipping 4. We're going to do 5, 6, 7, 12 together. So these are where the labs are. And now these page numbers are weird. And so it's kind of hard to find. So lab burner will be 1. And they'll go 1-1 through 1-whatever. All right, we go till what, 12:55 today? This lab's pretty short. So we'll start the lab in a little bit later. And you don't have to have the supplement in the lab book to do the lab. You could just write it in notebook paper. Did anybody buy the comp book yet? Yeah. If you have the comp book, leave the first page or 2 pages blank so we can make a table of contents. And so leave those blank and then take your observations for today's lab in the comp book, like on the third page. Let's say. Do that. We're going to go through it together, so you don't have to pre-read the procedure or anything like that. Okay, we're still good here. All right, so what I do is continue with our chapter 2 here. So we have models. Well, it's not the models like the ball and stick and the atoms known as spheres, that type of stuff. Chemistry's models of atoms, molecules that are based on experimental. It could be based on experimental, but most often it's based on theoretical because you can't actually see these things. You can see it experimentally using an STM or something like that, and so we could have a model like that. But it could be based on empirical data or it could be based on theoretical data. The simulations that I showed, those are called the molecular dynamic simulations, or theoretical models. And so we could approach it two-pronged. In fact, this is the advantage of approaching things two-pronged. Empirical are just facts. And so what do you do with facts? You have to memorize facts. How many facts do you want to memorize? There are too many facts to memorize. So we'd like to approach things theoretically because how much memorization do you have to do with theory? If you know the theory, did you have to memorize all the properties of the elements there? But by memorizing means observing and writing it down and remembering. Did you have to do that? No. For theory, we can minimize the amount of memorization. So the more theoretical knowledge we have, the better. But the problem is the theory is very complicated. The mathematics of the theory are very complicated. Those simulations were done on heavy, like heavy-duty, powerful computers. So, and not only that, there had to be some simplifications to the math in order to do those simulations. Remember, the math would be the mathematical definition is the most concise definition of those things. So the math is difficult. And so the best balance is a balance of both. The more theory we know, the less memorization we have to do. So the more theory, we'd be able to predict what the strong acids are based on 3 things, composition, structure, and ultimately properties. So if somebody gave you the composition, you'd figure out the structure and then figure out the properties. You wouldn't have to measure them. If you had to measure them, that would be data you'd have to remember or memorize. And so we do a two-pronged approach, experimental and theoretical approach. Maybe I should write some of this down. I could say and or because, two-pronged means both. We have different, in theoretical and experimental physics and chemistry, we have different types of calculations. Empirical calculation, totally based on observation. Semi-empirical is part observation, part theory. Ab initio calculations are 100% theory, that kind of thing. And so let me add that here. So I can get this. Do you know what the theory of chemistry is called? The theory of chemistry is called quantum mechanics, and it's the theory we use to try to predict things in chemistry, quantum mechanics. We're going to talk about quantum mechanics. That's what the quantum numbers was all about, quantum mechanics. All right, common molecular models, ball and stick. There's no sticks. They're just balls. The sticks are just separated so it doesn't all clutter up, so it's hard to see. These balls are what we call space filling. They occupy some volume. There's no stick. And so space filling is more accurate than ball and stick, but ball and stick are frequently shown. So this would be methane. This would be what we call a wedge dash diagram. This is trying to show it three-dimensionally because these molecules aren't always two-dimensional or one-dimensional like an atom. I guess molecules would have more than one atom. Molecules are two or more atoms bonded together. I mean, we have 4 hydrogens bonded to a carbon, so they're 5 atoms bonded together. But this, do you see, this is called the wedge. The wedge represents a stick sticking out like this. And a dash represents going in. So this is wedge dash. And these two are kind of in the plane of the paper. So these two would be in the plane. So this is a drawing trying to represent the three-dimensional structure of this ball and stick model. But this is methane. Methane has a formula, 1 carbon, 4 hydrogens. It's CH4. And we memorize this. Most people will find this one not too hard to memorize. It's just called methane. Natural gas is a mixture. In natural gas, it's mostly methane, a little bit of ethane, a little bit of propane, and some odorant. This natural gas. So this is a plastic ball and stick model. This would be a computer-generated image over here. Let's see if I think I'm going to have to buy a new one of these. Okay, there it goes. So ball and stick, but no sticks. This is more of the reality. Yeah. And so this is more of how it would appear to, let's say, a microscope or whatever you're using to probe it. And so this is methane. And this is a composite where they overlaid the space filling with the ball and stick so you could better see. You know, you better see, ball and stick is great for the angles. What are the angles between these hydrogens? These hydrogens here. When you do space filling, it's hard to see, you know, what are the angles here? That kind of stuff. So it's easy to see represented in ball and stick because what we want to know are 2 things. We want to know the length, you know, the distance between the centers of these spheres, here, this length, and we want to know the angle. Here. If we know the length and the angle, then we know the three-dimensional shape of it. And so we just need 2 things. So mathematically, 2 things will define methane, the length between the center of the spheres and the angle. Methane's a gas. Well, anyway, we have, what's this say here? This is model. We have chemical symbols representing the elements. The elements, you know, have 120 elements making up the physical material of the universe. But beyond that, we have things, subatomic particles too, representing the physical material of the universe. But for chemists, we focus mainly on just the elements here, not the protons, neutrons, whatever that might break off. So H represents hydrogen O, this is H2O. We've already talked about this. So when we look at the states of matter, when we look at it at the particulate level, this is a particulate level here. We look at kinetic. What does kinetic refer to? Motion energy. Kinetic energy. There are two types of energy. Well, there are more, but there are 2 types. The total energy of anything is the sum of its kinetic energy plus its potential energy. So if I want to know what is the energy of water, then there are 2 things I want to know. What is its kinetic energy and what is its potential energy? And then I know the energy of water. When we look at kinetic is motion, and kinetic energy applied to here will be molecules in motion. So kinetic molecular theory is the motion of these particles. the theory. And this is all like quantum based. So these are quantum based calculations. So even though it says kinetic molecular theory, this all comes from the theory chemistry, quantum mechanics. All matter consists of extremely tiny particles that are in constant motion. Unless it's at, zero, absolute zero. Do you know what absolute zero temperature is? Not 0 degrees C. At 0 degrees C, they're still moving a little bit. It's called 0 Kelvin. At 0 Kelvin, there's no molecular motion. And so temperature is a measure of the motion. If there's zero temperature, there's zero motion. Can you have negative motion? No. Motion is motion. Whether, what's moving back, what's moving forward, what's moving up, what's moving down, it's all relative. It doesn't really matter. So again, kinetic equals motion. And molecular comes from molecules. Molecules in motion. This motion, it's faster at higher temperatures and then slower at lower temperatures. So eventually the motion goes to zero. If we have zero motion, then we have zero temperature. However, if we have zero motion, we have zero temperature. We call this temperature absolute zero. It's not 0 degrees Celsius, it's not 0 degrees Fahrenheit. It is 0 Kelvin, which equals minus 273 degrees Celsius, which is equal to minus 454 degrees Fahrenheit. Minus 454. You can't get any colder than that. So is it possible to hit negative 300 Celsius? Impossible, because motion's already stopped. So when we look at matter, the first thing we look at is what is its state. Is it a gas? This is macroscopic. Is it a liquid? Is it a solid? Gas, liquid, or solid? And there are going to be physical characteristics between those. So the gases fill up the container volume. Like gaseous water molecules don't all sink to the bottom, whereas liquids will fill the bottom of the container. And solids just stay as is. They don't spread out to fill the container. The solids have rigid. And so this is one of the macroscopic properties we use to define a gas. The shape of a gas will be the shape of its container. The shape of water will be the bottom of the container. And a solid will just be whatever it froze into. So we define things at the macroscopic level, and we define things at the particulate level. So shape is one of the things we define at the macroscopic. We say a gas has variable shape, the same as its container. We say a liquid has variable shape, the same as the bottom of its container. A solid is rigid and fixed, so whatever you froze it into, that's going to be its shape. Now, the volume here of a gas can expand or contract. It can grow bigger or smaller, so that's why we call it variable. However, liquid volumes are not. And so one way we define this is compressible. Can you squeeze it down into smaller volume? For gases, you can squeeze them down into smaller volumes, although it takes work. But you can squeeze them down. And so you can force a lot of air into a small tank. But can you force a lot of water into a small tank? No, because water is what we call incompressible. And it's incompressible. Why are gases compressible and water incompressible? So at the particulate level, we can see why. Because at the particulate level, there's empty space between the water molecules. And so we can squeeze the water molecules closer together by just getting rid of some of this empty space, this distance between the molecules here. Whereas for liquids, is there a lot of empty space between the molecules here? No, the molecules are already touching one another. They're stuck to one another. So liquids are incompressible. You can compress them a tiny bit, but that's it. How about solids? Are solids compressible? No. And so what we say is if something's incompressible, it has constant volume. If something's compressible, it has variable volume. It could also expand, compress or expand. Now, looking at it in terms of particles, gases have completely independent, randomly moving particles. So the particles can go whichever way they want, left, right, up, down, it doesn't matter. Whereas liquids have independent particles, but they're stuck to one another, so they can do what we call translational. And so in kinetic molecular theory, we have three types of motion. And the first type of motion is called translational motion. Here, these can translate any direction, up, down, left, right, it doesn't matter. For water can also translate, but it's stuck in the liquid. The molecules are stuck together, so it's not going to translate up here, but it'll translate within the beaker here. Solids have no translational motion, so the water molecules are fixed. They're frozen in place. Whereas in liquid water, the molecules can actually move about. The next type of motion is called vibrational motion. And here, thinking of these as ball and stick is easier because the atoms themselves can vibrate relative to one another. As the water molecules, the hydrogens can vibrate back and forth. And so we'll have vibrational, translational, vibrational, and the third type of motion is called rotational motion. So in a gas, we have freedom to do translations, vibrations, and rotation. In a liquid, we have some restricted translational motion, but it can still vibrate and it can still rotate, although with more difficulty. In a solid, then there's no translational and there's no rotational, but there is vibrational. And so the atoms can just vibrate in place. And so these are the three types of motion. That we should remember. Here. All right, I'm going to stop here so we can do the next lab without too much time pressure. All right, this is the modern version of the Bunsen burner here. The original Bunsen burner didn't have some of the features we have on this one. And this has a name for the person who invented these additional features, but we don't have to worry about it. We're still just going to call it Bunsen burner. Now, the Bunsen burner is attached with this rubber tubing. This rubber tubing is for gas. And so this is a gas tubing, and it's kind of thick, so the gas didn't leak out. If the gas leaks out, we're going to have an explosion hazard. So do you know what the smell of gas is? Do you know the odor? If you don't know the odor, then let some gas bleed out. Don't let too much gas bleed out, because then that's an explosion hazard. But you can let some gas bleed out. It's not toxic. Methane's not toxic. You're not going to die from inhaling it. Well, you could, I guess, asphyxiate yourself. Or if you inhaled it and lit a match, you could die as well. But we're okay. So we have two types of valve. This valve is what we call a ball valve. what happened here. Alert. A ball valve. A ball valve has an arm. If the arm is parallel to the line, it's open. If the arm is perpendicular to the line, it's closed. So ball valve, you can easily see if the valve is closed, perpendicular, or open. And then you can adjust how much it opens by twisting it like this. It just has 90-degree range. And then we have these other valves, these ones that are twist valves here. Clockwise is closing, counterclockwise is opening, and how many turns you get will adjust it. Those ones are more difficult. Those ones you can't look at it and see if it's open or closed. And so sometimes people forget to shut that off and the whole room smells like methane, natural gas. Methane's odorless. So. All right, we should have enough Bunsen burners for most people, but if not, you can share with your neighbor. What we're going to do is we're going to disassemble. There are only 3 parts to this. There's the barrel. So get the barrel and turn it counterclockwise and then screw it off there. All right, take a look at the barrel. Do you see there are holes in the bottom of the barrel? Those holes are air inlets. So we can adjust the amount of air that goes in by screwing the barrel in or screwing the barrel out. That will adjust it. But look inside the barrel. Is there anything else? It's just a tube, right? With a screen at the top. The screen is to prevent garbage from clogging up the tube. All right. Now, take a look at the base of the burner. Do you see that little hole? That little hole is the orifice in which the natural gas comes out of that. So we have 2 valves. The ball valve or your twist valve there, and I should know the name of that valve, but that valve is for course control. So here, I usually open this like full open. And then this has another valve here called the needle valve. The needle valve is just for fine control. The needle valve is not used to shut on or off the gas. The supply valve is used to shut on or off the gas. Let's take a look at the needle valve. So go on the bottom of the base here and unscrew the needle valve out from the base.